Hope everybody had a nice and restful reading day. Hopefully you got to do some reading too. Go ahead and come on in, get comfy, and we'll be going in about 4 minutes. All right, gentlemen, welcome to Wabash After Dark. So, we're getting ready for an exam. So, we might as well keep practicing. We got to talk about demand functions and equilibrium bundles today. So, I decided I picked 3 different utility functions to look at, and these are going to be 3 of our less commonly seen ones because we need to make sure we're practicing these because a good chance at least 2 out of the 3 of these will show up in one way or another on the exam. So, let's make sure we get some practice in. As always, if you get some more questions while we're working on this, feel free to type them in chat, let me know, and we will keep going with them. So let me get that all set up real quick, make sure I'm looking at the right things, and we are ready to go. Let's jump into our first one. All right. So we have a utility function of x plus 4y to the 0.75 power. Now, before I was even done reading that, if you were looking at it, you should have immediately thought that this is quasi-linear utility, because that's a quasi-linear utility function. Now, also you should be thinking, okay, the the y in this quasi-linear utility function is our nonlinear term, which means that our consumer is going to want to consume some fixed proportion of good y first, and then anything extra beyond that fixed amount of good y, they're going to want to spend on good x. So we want to get good y first, then we want to get good x. Also, we can plug this in and do calculus just fine, but we have to check at the end to make sure x doesn't come out negative. So we got to go back and check, make sure we don't have a corner solution. So let's go for it. All right, we're going to plug and chug like we normally do. So let's set this one up. We're maximizing x and y. Our utility function, subject to, I got two sets of prices up here. We're going to do the first one first. 2x plus 3y equals 60. Okay, setting up the problem. Make sure we're organizing that information well. Next step, let's get a Lagrangian. And again, that is our objective function, 4y, 0.75, plus a Lagrange multiplier, and then we rearrange our budget constraint. Okay, that should also be getting pretty straightforward at this point. Next step, we've got first order conditions. Okay, derivative with respect to x. So there's an x in this first term, so the derivative of that is just 1, but there's no x in this second term. So we treat that as a constant, so the derivative of that is 0. So then we move over to our Lagrange multiplier. We got 0. We've got minus 2 lambda. And then again, like we do with every first order condition, we set it equal to 0. Okay? So remember, when we are dealing with derivatives of functions like quasi-linear, we need to make sure we're treating each term separately. The other term isn't just along for the ride like it is in Cobb-Douglas. Next, we take the derivative of our Lagrangian with respect to y. And again, there's an x in the first term, there's no y, so we treat that like a constant, so the derivative of that with respect to y is 0. Then we do the next term, 0.75 times 4 is 3, y, subtract 1, negative 0.25. Move over to our constraint, and we get a oh man, it's jumping all over the place today. Minus 3 lambda, and again, we set that equal to 0. And then, as always, the derivative of our Lagrangian with respect to our Lagrange multiplier is just equal to our constraint. That is our easy one right there. So, like every situation we've done so far with consumer theory, and it's not changing anytime soon, we've got 3 equations, 3 unknowns, and we just got to solve this. It's always easier to start with our first two first-order conditions. So move everything with a lambda onto the right-hand side. 1 equals 2 lambda, and we got 3y to the negative 0.25 equals 3 lambda. Take the first one, divide it by the second one. 1 over 3y to the negative 0.25 equals 2 lambda over 3 lambda. When we do that, the lambdas cancel out, and that's what we wanted to do. We're also going to find that the 3's cancel out too. Excellent. So this is going to tell me I can rewrite this y to the 1 over y to the negative 0.25 as y to the 0.25, just get rid of that negative exponent right there, equals 2. So what's really neat about quasi-linear utility functions, and again, this is our tangency condition right here. What's really neat about that with quasi-linear utility functions is that the tangency condition is only going to be a function of one of our choice variables, specifically the non-linear choice variable, which of course is y in this situation. So normally if we were doing a Cobb-Douglas, we'd go back, plug this into the third first order condition and go from there, but we don't have to. We can solve for y directly. And the way we're going to solve for y is we're going to raise both of these to the 4th power, because y to the 0.25 to the 4th power equals y. And so that equals 2 to the 4th power. And let's see, 2, 4, 8, 16. That equals 16. So I know that regardless of my prices or my income, well actually it is based on the prices as well. I should take that back. Regardless of my income, I want to consume 16 units of good y in equilibrium. Okay, that is the sweet spot. I don't want to consume any more. It doesn't matter how much extra money you give me. I just want 16 units of good y. And the way I'm going to get good x is I'm going to go back to this third first order condition. So I have 60 minus 2x minus 3y equals 0. Let's say 2x equals 60 minus 3. Hey, there's my y. Plug in 16. So let's see. 60 minus 3 times 16. 3 times 16 is 48. And so 60 minus that is 12. So x star equals 6. So right then and there, I have my equilibrium bundle. X star, y star equals 616. And we're done. So quasi-linear is great. Now the good news is, of course, with this one, is that this came out positive. So when our linear term comes out positive in quasi-linear utility, we are done. We don't have to do anything special because we do not have a corner solution. So we don't have to worry about that one, and that's our best case scenario right there. But that's it. That is a quasi-linear utility function, how we solve it, how we get our equilibrium bundle. So let's do it one more time now. This time I'm going to give you a little bit, only thing I'm changing is the income. So let's do it again. All right, so we have max x, y, and that was what? X plus 4y to the 0.75 power. Subject to, it was 2x plus 3y now equals 30. 2x plus 3y equals 30. Okay, Lagrangian time. I'm going to go through this quickly because you're going to see that a whole bunch of this is going to be exactly the same. In fact, only one number is going to change. So I'm going to go real quick. X plus 4y to the 0.75 plus lambda. 30, that's the only number that's changed, minus 2x minus 3y. Get some first order conditions. The derivative of Lagrangian with respect to x is 1 minus 2 lambda equals 0. Derivative of our Lagrangian with respect to y equals 3y to the negative 0.25 minus 3 lambda equals 0. And lastly, of course, the derivative of our Lagrangian with respect to our Lagrange multiplier, it's still just our constraint, set equal to 0. So notice when we compare these first order conditions to our previous set of first order conditions, these first two are actually identical. Nothing at all has changed about them. Whoa, what just happened here? I don't want that. Thank you. All right. I don't know what just happened right there. So these first two first order conditions are completely identical. And that means all these calculations over here are going to come out the same. I could set them up and go do them, but with these two equations being exactly the same, I know right away that y star is going to come out as 16 because those equations are exactly the same as last time. So I'm gonna save. I'm gonna write same two first order conditions. So it's gonna give me y equals 16 again. Now let's go back and plug it into here, into our third one. This is where things are going to get a little different. So 2x equals 30 minus 3 times y, which of course y is 16. Let me erase that real quick. So I get 2x equals negative 18, or x star equals negative 9. Okay, x came out negative, and this is a problem right here. So what this is saying, and actually you can kind of look at this, we want to consume 16 units of good y, regardless of what our income is. The only problem is, in order to consume 16 units of good y, I'm going to need $48 because the price of good y is 3. I've only got $30, so I don't have enough money to even get my minimum desired level of good y. And because of that, my linear good comes out negative. So what this is actually telling us is that if we could just sell some of good X, even though we don't have any of it? We would. We would sell 9 units of good X in order to buy the rest of good Y that we want. But it's not like GameStop. We can't sell shorts that we don't actually have. So we're stuck right here. And what this means is if our linear term comes out negative, that's going to imply that it's actually equal to 0. We're in a corner solution. We aren't going to consume any of good X at all. But if that comes out at 0, we have to redo our Y. It means that the amount of good Y that we're going to consume is just our income divided by the price of good Y. It's how much money we have divided by the price. It's basically we're going to spend all of our money on good Y, and we're going to buy as much of it as we can. So that's just our income divided by the price of good Y. So that's 30 over 3, which equals 10. And so our equilibrium bundle in this case is equal to 0, 10. And that's quasi-linear utility, gentlemen. So remember, when you set it up, do your calculus like normal. The only thing you got to watch out for is if the linear term comes out negative. If the linear term comes out negative, then you have to adjust. Okay? But that's the trick right there. All right. Ooh, that's a good one. Now, if you look in the repository, there's a very good quasi-linear problem in there that I asked on the exam last semester. Work on it this weekend. I want you to have class from tomorrow before you work on it because it's definitely got a corner solution in it and it's quite challenging, but it was a great problem. Okay, let's do the next one. All right, new utility function. Our utility of x and y equals 2x plus 5y. Now, by the time it took me to read that, you should be able to tell me that's perfect substitutes. Both our x term and our y term are linear. They're added together, so these two products are perfect substitutes. We like good y better because it gives us more utility. So what I don't want to see on the exam is you try to do calculus on this because it is a waste of your time. We don't want to do calculus on this because when we have perfect substitutes, we know that we're either going to want to spend all of our money on good x or all of our money on good y. Nothing in between. So the way we're going to figure out which one we're buying, it's either all of good x or all of good y, we're going to figure out which one gives us the most utility. So, all right, for the first one, if I get x, so it's going to be y over px. I spend as much money as I can on good x. So that's 100 over 1. That's 100 because the price of good x is 1. If I go y, that's y over py. So 100 over 10, that equals 10. So let's plug these into our utility functions. If I get just good x, so if I put in 100 for x and 0 for y, that's 2 times 100 plus 5 times 0. And that equals a utility level of 200. So if I only buy good x and I don't buy good y, I'm going to get a utility level of 200. Seems pretty nice to me. But if I only buy good y, now I can only get 10 units of good y because of the price, I get 0, or no, sorry, that's 2. It's going to come out to 0. 2 times 0 plus 5 times 10. So I'm going to get a utility level of 50. So right then and there, I can tell you that I'll get more utility if I spend all of my money on good X than I will if I spend all my money on good Y. So right away, I'm done. I'm going to buy all of good X and none of good Y. That's it. That's a perfect substitutes problem right there. You just figure out which one gives you the highest utility. Figure out what your utility would be if you just buy good X, what your utility would be if you just buy good Y. Plug them in the utility function. Pick which one gives you the higher value. Okay, well, that was the first version. Let's try the second one. Okay, now the price of good X is 5. Okay, so once again, X equals Y over PX. 100 over 5 now, because the price went up. We can only get 20 units. Y equals Y over PY, and of course that's Y in income. 100 over 10, and that equals 10. My utility from 20, 0, because I can only afford 20 units of good x now, is equal to 2 times 20 plus 5 times 0, so that equals 40. My utility, if I don't buy any good x and I buy good y, 2 times 0 plus 5 times 10, which equals 50. So before, kind of like how we liked good x, now we like good y. That's the better one. It gives us the higher utility. And so our equilibrium bundle, we're done here. None of good x and as much as we can of good y. And that's it. That's a perfect substitutes problem right there, gentlemen. So like I was saying, trying to set up a utility maximization problem here, completely unnecessary. And honestly, it's not going to tell you anything unless you memorize a whole bunch of rules that you really don't need to memorize. All you got to do, you know it's going to be one solution or the other, try them both, see which one gives you the highest utility, and you're done. That's the, what I think of is the best way to solve these problems. Okay, that's it. That one went real fast because, of course, we don't have to do utility maximization for it. Well, let's do a third one. All right. Okay, the utility of x and y is the minimum of 3x and y. And once again, you should have seen that right away and said, that's perfect complements. We know that our consumer is going to want to consume these two goods in a fixed proportion. We also know that we can't use calculus on this one because we can't take the derivative of that function. It just isn't going to work. But there's a saving grace. We may not be able to get a tangency condition, but we know this fixed proportion is going to hold. And in fact, that fixed proportion is we just set these two terms equal to one another. 3x equals y. So I know I'm going to consume 3 times as much of good y as I will good x in equilibrium. And we can use that to help us. Because if I take this fixed proportion and I take my demand function, it tells me to derive a demand function first, so I don't have price or quantities yet. I have pxx plus pyy equals my income. I can just substitute this in. And in fact, I'm going to plug it in right here for y. So I get pxx plus py 3x equals my income. So this can be a little bit of nasty algebra, but you should remember if we're dealing with perfect complements that you're going to have to factor the left-hand side of this equation. Anticipate that. We got to factor the x out of here. So I'm going to have x times px plus 3py equals my income. And then I just divide by this term in the parentheses here, and I get my demand function for good x as y over px plus 3py. And that's it. That's our demand function for good x. So once again, when we're dealing with perfect complements, we don't have to set up that Lagrangian. We don't have to do any of that stuff. It's just quicker and actually easier to just jump to that fixed proportion. And really, we can't even set up the Lagrangian because we can't use calculus on this. Next, we got to get y, which I know from my fixed proportion is 3x. And look at this. I just put a 3 on top, and I'm done. Easy enough, gentlemen. Okay, so there's demand functions. Well, now I have prices. But lo and behold, I just derived demand functions, so I don't need to go back and calculate any of this again. I can just plug those values into my demand functions and get my equilibrium bundle. So x star is equal to 100 over 4 plus 3 times 7. So 3 times 7 is 21, plus 4 is 25. 100 divided by 25 is 4. Y star, which of course I know is 3 times x, but still, should come out as 12. 3 times 100 over 4 plus 3 times 7. So that's 300 over 25, which is, of course, 12. And that's it. Our equilibrium bundle, x star, y star, is 4 and 12. Okay, wow. We got through those problems a lot faster than I thought we would. But still, these are the things that you want to make sure you're getting very comfortable with as we approach our second exam, okay? You want to get to the point where you just look at a utility function and you honestly don't even have to take time to process what kind of utility am I looking at. You should be able to recognize Cobb-Douglas. You should be able to recognize perfect substitutes, perfect complements, and quasi-linear utility. Now, there are more utility functions than that, but those are the four that are going to show up for your exam, okay? And probably, 95% of the time, those are the four you're going to use. So recognize them and then instantly remember the rules that are associated with each of those types of utility function. So with Cobb-Douglas, we plug and chug. Set up your Lagrangian, maximize it, you're good to go from there. For quasi-linear, we plug and chug, but we got to make sure we check that linear term in case it comes out negative. If it comes out negative, we've got a corner solution. Perfect substitutes. Do not use calculus at all because the calculus is not going to help you. Okay? You know it's going to be one corner or the other corner, so figure out which one gives you the highest utility and then pick the one that gives you the highest utility. And of course, lastly, perfect complements. Can't use calculus on that one because it's not differentiable, but we do know that we're going to consume in a fixed proportion. And so we can leverage that fixed proportion in order to help us find our equilibrium. All right, gentlemen, that's all I got for today. So let me open it up for a moment or two to see if there's any other questions we want to talk about. And if not, we will call it here for today. While I'm waiting real quick, I am thinking that we're going to do 2 Wabash After Dark sessions next week. We're going to do a session on Tuesday to review income and substitution effects because that topic needs its own session. Yeah, we gotta practice those for the exam because they're showing up on the exam. And then Thursday of next week we will do our standard exam review session. All right. So I'm not seeing any questions, so we are going to call it here for today, a nice short session. So gentlemen, keep practicing. We have exam 2 in 8 days, and I'll see you guys in class tomorrow. Enjoy the rest of your reading day, and I'll catch you next time.